Hello everybody. Welcome to the visual lectures on mathematical physics. I am Hank Nozawa. In this video, I am going to tell you an introduction of the principle of Lagrange multiplier method. This method is used to find the value of variables which gives a maximum or a minimum value or stationary value of a given function. Let fxy be a given function of x and y, where x and y are not independent but have to satisfy a relation between x and y that we call a function gxy equals 0. Lagrange multiplier method is very useful to find stationary value of fxy under this constrained condition gxy equals 0. Simply speaking, this method is to define a new function lxy circled by red and then to solve the three equations circled by blue. Although in this video we handle only two variables for simplicity, the true power of this method will be seen when we need to handle many variables. This method is the easiest and most convenient way to solve the problem of many variables. Before learning Lagrange multiplier method, let's consider the next problem. Imagine two functions fxy and gxy on the xy plane. For those two functions, we can imagine two curved surfaces f and g in the xyz space, where z-axis indicates value of fxy or gxy. And if we compare these surfaces to two mountains, we can draw the counter lines for each surfaces. The counter lines of f and g can be drawn independently. So generally, counter lines from f and g intersect each other. But sometimes they don't intersect, but they just come in contact. What we are interested in is those points where counter lines of f and g contact each other. Let's figure out the equation to find those contact points. If the area of contact point for surface G is magnified, we get the slope ABC, for example, as shown like this figure. In this figure, line AB represents a counterline. And then we can add another slope ABD from the surface F to this figure. In this figure, line AB again represents the counterline of this area. The reason why line AB shares for both the slope G and F is because two counterlines of F and G contact each other. When the two slopes have such a relation, the ratio of the two angles of the inclination of the slopes in x direction is exactly the same as that of in y direction. In other words, if the inclination of f is lambda times that of g, as regards to x direction, the inclination of f is also lambda times that of g as regards to y direction as well. So we can define lambda by the equation delta f divided by delta g equal lambda, where delta f and delta g are as shown in this figure. And also in this figure, delta x and delta y are also defined as well. The definition of lambda is also written as delta f minus lambda times delta g equals 0. The reason that lambda is defined this way is very important to understand this method. This is simply because the counter lines of f and g contact each other. If they are not contacted, there is no meaning to write this way. There is even no way to express delta x and delta y in a common sign for both surface f and g. So, if the counter lines do not contact but intersect, the ratio of the inclination of slope f and slope g cannot be expressed using only one parameter lambda for both directions at the same time. Let's define a new function Lxy as framed by red. At a point where counter lines of f and g contact, the derivative of Lxy by x becomes 0 owing to the definition of lambda, and also the derivative by y becomes 0 as well. Needless to say, this 0 means the surface Lxy is horizontal at this small area. You can also imagine this. At the point where the counter lines contact, if a very small piece cut off from surface G is multiplied by lambda in z direction, it can become exactly the same as that from the surface f. So if you take the difference of f and g times lambda, it becomes 0. This is the reason that this small area from L is horizontal. In brief, by choosing lambda adequately, the curved surface Lxy can be horizontal at the point where counter lines of f and g contact each other. The important thing is that the same value of lambda is used for both x and y direction. Although the value of lambda can be obtained numerically, it is not necessary to do this, because the purpose of introducing lambda is only to find the point where counter lines contact. In other words, the reason that the parameter lambda is introduced is not because we need the value of lambda, but because we want to express the conditional equation that counter lines contact each other. And this purpose is accomplished already by using the same value lambda for both x and y directions. Let's return to the method of Lagrange multiplier. There is a function fxy of two variables where x and y are not free at the same time but have to satisfy constraint conditions gxy equals 0. Under this condition, the Lagrange multiplier method gives an answer to find a point xy where function gxy takes stationary value. If the curved surface G drawn on xy plane is compared to the mountain, the constraint condition gxy equals 0 is equivalent to the counter line of sea level equals 0. And on the xy plane there is another mountain called f, but when a point xy moves along the curve gxy equals 0, the point xy goes up and down the mountain f. However, sometimes it is possible to move without up and down the mountain, but moves horizontally. That is along a counter line of f. In other words, this counter line is contacting with gxy equals 0. This point gives stationary value and is right the point that we are trying to find out. In brief, Lagrange multiplier method resembles very much with the problem to find a point where counter lines of the mountain f and g contact each other. The difference is the only one counter line gxy equals 0 is in question for surface G. in considering Lagrange multiplier method. So if a function Lxy is defined as shown in a red frame when gxy equals 0, the partial differential of Lxy by lambda becomes 0. Needless to say, on the line of gxy equals 0, the value of lambda times gxy equals 0 and does not change even if lambda changes, because lambda is a coefficient to have an effect to let curved surface G merely expand in z direction. For such a reason, del x del lambda equals 0 is equivalent to gxy equals 0. Then, summing up the above, we get the Lagrange multiplier method. In brief, in order to find a point xy where a function xy takes stationary value under the condition gxy equals 0, as described before, firstly solve these two equations. Del x del x equals 0 and del L del y equals 0, which are the conditions that counterlines contact each other. And secondly, the equation del L del lambda equals 0 should be added. So we get the Lagrange multiplier method. Here again, you can determine the value lambda if you want, but actually it is not necessary to find how much lambda is, because the purpose to introduce lambda has been accomplished by using the same value in the first two equations, and the problem can be solved even if lambda is not determined. This is very important to understand the principle of Lagrange multiplier method. These are an introduction of the explanation about the Lagrange multiplier method. But to help you understand more, let me give you the image, a graphic meaning of a function Lxy. The flat area of surface L expresses where a counterline of surface G touches that of surface F. With a change of lambda, surface L changes its form, and it will be observed that the flat area appear and disappear at different places, like mole bushing. At that time, generally the height of Lxy changes too. However, sometimes height of surface Lxy may remain constant even if lambda changes. That is exactly the point that we seek the answer. This is the end of the video. See you again.